Well, obviously, most people were expecting that I was going to talk about short crack, and I'm not going to disappoint you, right? The topic of the conference is the characterization of crack tip stress field, as everybody knows. And when you think in terms of fatigue, the famous Paris law is the prime example of a very successful theory where one parameter characterization works. Now, if you analyze using dimensional analysis arguments the growth of a crack by fatigue, well, you have to consider, for example, a geometry like a very big component with a crack, and you need to put some plasticity in there because otherwise you cannot have growth by fatigue. Well, if you do this dimensional analysis, you end up showing that the crack growth rate can be expressed in this way. It's the constant, delta K, and then you also have the influence of the only two dimensions that we're seeing in the problem, which is the crack length itself and a new length which encompasses also the plastic zone. If this is the growth of a crack in an infinite medium, there are only two lengths there, so it makes sense that they should appear. But if you think in terms of the Dugdale relationship, this relation between the two lengths is connected to the applied stress and perhaps the yield stress. When you are dealing with low cyclic loads, sufficiently low to apply linear elastic fracture mechanics, it turns out that this ratio here is below 0.3, and then the Dugdale relation says that this is approximately between 0.9 and 1. So in this case, you really have the Paris law, right? This is something which is quite well known. The important thing here is that Dugdale relationship really describes the similar growth of the crack, right? When you have this crack growing in this infinite medium, you always have the same problem. It's just a question of changing the scale, right? And it's only when you have this subsimilar growth that the single parameter characterization is valid. If in the problem that we're considering the applied loads are a bit higher, we have a substantial plastic zone, and in this case, obviously, the term A over C should be taken into account, and then Paris law ceases to be valid, and you have to have another parameter. Now, another situation when you have a problem where subsimilarity is not preserved is the growth of short cracks, right? In there, most people know that the crack is growing and the plastic zone is stopped in some kind of barrier. I like to think that the grain boundary pattern, the most important barriers. And then you observe that the crack, the interface of the plastic zone is stopped while the crack is growing. So obviously this coefficient is not constant. And then you have not subsimilarity, right? In this problem, what is important is not the physical size of the crack. It's really the relationship between the crack length and the microstructure. And what I would like to show you today here is precisely that you can have short crack growth even when your cracks are very big, right? So what we're going to do is to show experiments that we've done in Seville with cracks that are very long, of the order of millimeters or centimeters, but still display short crack behavior, right? Before going into that, it may be helpful if I tell you about the motivation of this work. Well, some people here know that I've been doing models for short crack growth for most of my working life, really, and we've applied that to the problem of crack growing from notches. When you try to predict the notch fatigue life of a component, there are different sort of competing theories that allow you to do that. Nowadays, the most popular theories are the critical distance theories, and well, Lucas Sussman is one of the main exponents of this school of thought. But there are older theories like Peterson or Neuberg, notch sensitivity ideas. Now, when we were trying to apply the short crack growth model to the notch problem, we realized that all of the theories sort of give the same predictions when you work with components where the notch is much bigger than the microstructure. In the horizontal axis, sorry, this is in Spanish, I couldn't change it. This is the ratio between the size of the notch and the size of the microstructure. So that would be, for example, in the case of a hole, that would be the diameter of the hole divided by the grain size of the material. Now, when you deal with normal components, obviously the notches that you have are quite big, of the order of perhaps millimeters, and the microstructure for a normal material would be of the order of, I don't know, 50 microns. So you're really in this region here. And in here, all the theories basically gave the same prediction. For the case of a hole in a big plate, the notch fatigue limit would be approximately the fatigue limit of the material divided by 3, which is the stress concentration factor for the hole, right? We realized that these theories give different predictions when you move in this region here, right? It means that you're moving in a region where the size of the notch is becoming smaller compared with the microstructure. And the main differences should occur in this region here, where you have the notch size of the same order of the microstructure. So we decided that we have to go and try to look what happened here, which meant that we had to do very, very small holes if we were to work with normal materials. Since this is very difficult, we took the other way. We decided to manufacture a very big microstructure, right? So this is what we did in Seville. We use a certain treatment that I want to tell you now to produce very big grains so that we can actually drill the holes inside the grains, right? So the motivation so far is purely academic in a way. But later on we found that there are a number of practical applications with this kind of ideas and technique that we're developing may be helpful. For example, this thing here is a tube of a heat exchanger used in combustion engines. And what you have here is a tube, and inside you have a fin which is have a complicated shape, and you put the gases of the motor through here, and then you have water in the outside, and you use that to refrigerate the gases. Now, the thickness of this tube is of the order of 0.2 millimeters, and the fin is less than 1/10 of a millimeter. And well, the thing is that when this is used, you have fatigue problems here, and you can see the cracks that will sort of go through the tube, and then you have gas escaping into the water, and well, this is a big problem there. And there are some other examples that I could mention. For example, very small components used in microelectronics and in medical devices. For example, the stent that you use to open the arteries when you have a heart attack. This is a very small sort of spring made of very thin wires of titanium or stainless steel. We're talking about wires which are only perhaps 100 microns in size, right? So this kind of practical motivations gave more impetus to our idea of see what happens when you want to study the behavior of components where dimensions are not too much bigger than the microstructure, right? So we went for this idea and decided to manufacture these big grains. In order to do so, we used pure commercial aluminum, and we introduced some heat treatments. Initially, we heat the material up to 550 degrees and keep it there for 5 hours. Then we cool it. Do a heat treatment, mechanical treatment, which basically is putting the specimens in the machine and produce some plastic deformation, and then unloading. And then we go for a second heat treatment, which we heat it again at 550. We leave it here for 15 hours, and then we raise the temperature a little bit and leave it for an hour just to reabsorb small grains. Okay? This is the things that we actually obtain. The parameter that determines the final grain size that you will obtain is the intermediate heat mechanical treatment. So the level of deformation that you apply would result in a different size of the microstructure. You can see here that we have very small grains when we apply high plastic strain, and we can come up with these very big grains here, right? So the first thing they had to do is to characterize these microstructures, and this is done. We get the samples, we sort of mark the grain boundaries, and then with open source software like Simagis or ImageJ programs, you can actually calculate the grain size distribution, and this is the kind of things we're getting, right? So depending on the level of applied strain of the certain treatment, we have this thing. Just to give you an idea of, when the size of the microstructure is very small, we use normal electron microscopy with backscatter diffraction. This is the kind of result we get. We plot here the grain size, and we plot here the level of strain that we apply in the mechanical treatment. And we see that we need a certain threshold of the applied strain in order to change the original microstructure of the material. But then, once you overcome that, you get this sort of behavior. In here, we have different statistics here. This is the mode, the median, and the average value. These are not the standard deviation of the mean. I mean, the standard deviation of the mean is so small that it gets inside the point, right? So this means that the treatment is very reproducible. It's very easy to decide which is the size of the microstructure that you want, and you come to this graph, decide, find out the strain that you need, and then you get the microstructure that you want. So it's very reproducible and very stable, right? Here you can see the whole range of variation that we obtain. This belongs to the material as received originally without any treatment, and this corresponds to one of the treatments that produced the biggest grains, right? So we prepare the material in this way, and then what we do is we manufacture the notch specimen to get the crack started. So we get the specimen and drill the hole, and in this case here you can see a hole of 400 microns diameter, but as we can get grains as big as we want, we can drill different notch sizes. Right, this is the experimental setup. Let me see if I can go to the video. And hopefully it will work. You can see the specimen. This is just two cheap cameras. Mine are cheaper than the ones that David Nowell used. They cost me only €6, and he was talking about €20. And of course we don't have the Questa because we don't need it anymore, which means that this experimental setup is much more cheap than the one they're using in Oxford, which is appropriate because Seville University is a much poorer university. We're equally old, but we are much poorer, so that's what we expect. Right? Now, the system is so cheap and that you can actually record how the crack grows. And what I want to show now is how this is done. But I have to change again to a PowerPoint presentation, which I hate because I use LaTeX, but I couldn't find how to put that in LaTeX. This is moving, and then you will see the crack there. So what we've done here is we've got the same size for the hole, and we've produced this hole in different microstructural sizes. So doing that, you can see the whole behavior from long cracks to short cracks, microstructural short crack, right? In this case, the microstructure is very small; it's only 60 microns, and then what you get the crack growing mainly in mode 1 from the beginning. And when you see here, this is the typical thing that you get for a long crack, right? If we go for bigger, this is the final crack. If you go for a bigger microstructure, and we're going now for 1.41 millimeters, you will see the crack growing there. You can see here. By the way, this is the specimen when you view with the two cameras, one side and the other. But the image is rotated so that we are seeing here the same size of the notch in both of them, right? And you can see the crack growing and that. And when you represent the crack here, then you start to see this kind of behavior that corresponds to short crack, right? So we have in there cracks that are about 3 or 4 millimeters, but still are displaying the short crack behavior, obviously. If you go for the last one, now the grain is 3.46 millimeters. By the way, my student Pablo Lorenzino is the one who's done all these experiments, and he's got some of the specimens with him. All right, okay. Right. So in here you see that again we are starting to have this sort of thing, and you start to see all sort of complicated behavior. For example, in here we have a crack that branches, and you have to represent the crack growth of the different branches. And let me go, I think, to the last one. Now we're growing in about 1 centimeter grain. Okay? The hole is still 2 millimeters, and then you have a very large, very long short crack growing here. That's it that we want to demonstrate. Right? Now, which are the things that we're seeing here? You can see here the crack, and you see the crack growing in a sort of single slip system, and it stops at the boundary. I mean, it displays all the things that we know from previous work. Okay? The morphologies of the crack that you get is very interesting. Yes. If you plot the crack growth rate in terms of the crack length, you find a reasonable correlation between the position of the minima in crack growth rate and the grain size, right? As you would expect. So smaller grain have more places where they sort of halt, and bigger grains, obviously, have less of them. Okay. We also found quite curious behavior is you can see a kind of interaction between the two sides of the crack. And in here, this crack started growing in the right side, while the one on the left was stopped. But then when the crack growth rate of the one on the right diminished, this suddenly started growing. It's like they are not growing at the same time. It's like one is waiting for the other to stop to start growing, which is quite interesting. Well, this is the same, so I just stopped. Well, you have all sorts of very complicated behavior. Jaroslav was talking about crack closure before. I think you said that you don't expect much crack closure in short cracks. Well, it's the other way around, I think. You can see that here. The crack morphology is so complicated that you have this very striking example of crack closure. This thing here is impeding the upper part of going up, and it exerts some force here that has actually initiated this secondary crack here, right? So it's like you can have some tensile stresses pulling the crack faces when you try to separate it, right? Which is something that I find interesting. And look in here, you have the same. Can you see that? So it's not just that the crack faces are going to touch before the crack close. It's that when you start applying load, these sort of things will pull the crack faces and will refrain them from separating too early. Okay? It's like you have some kind of crashes there. Right? Well, we also see both single slip behavior and multiple slip behavior. You know, in this crack, you can see here the different things, right? And also we can see that we have non-damaging notches. When the size of the hole is sufficiently small with respect to the grain size, the hole doesn't play any role in the fracture by fatigue of the specimen. You have cracks growing somewhere else. Perhaps this grain was better oriented than this one, and the test concentration here, which is of the order of 3, doesn't make any difference for the crack to grow. All right? So you have all sorts of complicated behavior there. And now this another question that I would like to ask. Is there such a thing as a crack plane? You can see here the crack inside of the hole. And you can see the very complicated morphology that the crack has. In fact, if you were careful when we were seeing the animated GIF that I gave before, you can have a crack in one of the sides of the specimen going down and in the other side of the specimen going up. So if there is a crack plane, that would be completely inclined to the specimen. Of course, these specimens are very thin, because the specimen is, some of them are 4 millimeter thick, and some are just 2 millimeters. And we have grains that go from across the whole thickness of the specimen. So in this kind of situation, we would expect that the maximum shear stress plane would be inclined in that direction. So we were expecting this sort of things, but certainly not this kind of thing here, right? It's really complicated. Okay. Now, we did some investigations to see where the crack initiated. Although we know that we don't have a single crack plane, as I said before, some of the things that we were studying with our short crack models applied to notches tell us that we should not expect that the crack will always start in the plane of maximum load. We found out with our models that the role, the size of the hole compared with the microstructure has something to say about where the crack will be initiated. So we were investigating that here. And what Pablo did was got all the photographs here and started calculating or measuring the angle where the crack would start in each side of the specimen, right? He did a lot of measurements that I will go fast through it. And the results are like that. When we have holes that are small compared with the microstructure, the position of the point where the crack will start is very wide, right? And you have this kind of statistical distribution. This is for a microstructure of 0.94 millimeters, and we have holes of different size. And this is much better view here. This is the same microstructure, and this is the different size of the hole that we tried. And what we see is that as the hole gets bigger compared with the microstructure, the region where the cracks initiate diminishes. In here we are about 30 degrees, and in here we have 50 degrees, right? And you have here the different statistical distribution that we have. So the bigger the hole, the more likely you are to have the initiation point closer to the plane of symmetry. But when you go for holes that are smaller and smaller, you end up having more possibilities of initiating the crack in different positions of the hole. And as I said before, this is something that we have seen in our models, but of course our models is very simplified, and it's hard to compare with what's here, right? Well, just to finish the talk off, I would like to tell you what we are doing now is we are trying to use digital image correlation to actually follow the whole growth of the crack. And what Pablo has done is he's got a system whereby he can attach the cameras through little plastic cones in here to the specimen. So you can record continuously while the crack is growing and the specimen is moving. But because you have the two cameras on top of the specimen, you eliminate a lot of problems, and then you can have very good results. Let me show you the next. This is something that we've just started, so we haven't done much quantitative analysis of the results that we got with this thing. Okay, but you can see how the specimen is being loaded and unloaded, and how we have everything there. Of course, the thing that we are getting is I don't know how to start the presentation from here. Well, it doesn't matter. It was just to show that.
Yeah, check the box down below where your cursor is.
This thing?
No,
the one with the
This thing?
the one next to 38.
yeah, the one with the this with the
This
that's
thing?
it,
That
that's
one,
it,
yeah.
that's it, yeah.
Right. Well, just wanted to show the last picture, so it doesn't matter. I have some videos, but I don't think it's worth showing that here. So this is all. This is the way in which we've been studying the growth of very long short cracks.